Lucky Land Slots, you can get lucky just about anywhere.
Dearly beloved, we are gathered here today to... Has anyone seen the bride and groom?
Sorry, we're here. We were getting lucky in the limo and we lost track of time.
No, Lucky Land Casino, with cash prizes that add up quicker than a guest registry.
In that case, I pronounce you lucky.
Play for free at LuckyLandSlots.com. Daily bonuses are waiting. No purchase necessary. Void where prohibited by law. 18+. Terms and conditions apply. See website for details.
Hello, it is Ryan, and I was on a flight the other day playing one of my favorite social spin slot games on ChumbaCasino.com. I looked over at the person sitting next to me, and you know what they were doing? They were also playing Chumba Casino. Coincidence? I think not. Everybody's loving having fun with it. Chumba Casino is home to hundreds of casino-style games that you can play for free anytime, anywhere, even at 30,000 feet. So sign up now at ChumbaCasino.com to claim your free welcome bonus. That's ChumbaCasino.com and live the Chumba life.
No purchase necessary. VGW. Void where prohibited by law. See terms and conditions. 18+.
This episode is distributed under a Creative Commons Attribution Share-alike 4.0 international license. For more information, visit creativecommons.org.
This is Gabriel Hesch from the Breaking Math Podcast. I am thrilled to announce that we have teamed up with a particle physicist and a science fiction author named Dr. Alex Alanis to create a brand new science show on YouTube. Our new show is called the Turing Rabbit Holes Podcast. It's named after the mathematician and father of modern computer science, Alan Turing. You can find us at youtube.com/Turing Rabbit Holes Podcast, and that's spelled Turing Rabbit Holes Podcast. Be sure to like and subscribe for great visual storytelling about the history of mathematics, physics, and computer science and the impact that they have had on society. Again, that's youtube.com/Turing Rabbit Holes Podcast. And now, back to the Breaking Math Podcast. Somebody stole our website.
Oh no, whatever shall we do?
I mean, I guess you could go to the new website, http://breakingmathpodcast.app with no www for all you old timers.
So breakingmathpodcast.app? I mean, if you're into that sort of thing.
A, B, 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 A, B. How much information was that? You may say 16 letters worth, but is that the true answer? You could describe what you just heard as AB 8 times, and save a bunch of characters, and yet have the same information. But what is information in the context of mathematics? The answer is nothing short of miraculous. Information theory has applications in telephony, human language, and even physics. So what is information theory, and what can we learn from it? All of this and more on this episode of Breaking Math. Episode 3, TMI. I'm Jonathan Baca.
And I am Gabriel Hesch.
And you're listening to Breaking Math. And today with us we have...
Gideon, dilettante of the odd.
And also we have...
Hannah Butler, recent math graduate.
And today we're talking about information theory. Now, Gabriel, what is the essence of information theory?
Okay, so the essence of information theory is basically saying that everything in the universe can be also described in terms of information. That is, in terms of bits.
Exactly. And a bit is a yes or no choice that is fair. That is how much information is contained in one bit. But we have a few constraints that we need to put on information. First of all, we need to have it seem like our intuitive concept of information. That's to say, if we have 2 pages, it can contain twice as much information as 1 page, basically. It seems self-evident, but that's a huge constraint. And that's what Claude Shannon, the father of information theory, as he's known, designed the formulas around.
Yeah, and in fact, now we don't hear a whole lot about information theory as a concept. I would say until you're, in my experience, at least a grad student in engineering, well, some of the higher level classes as an undergraduate, you definitely hear it if you're in communications. Now, Claude Shannon is the mathematician and the engineer who, is, as you just said, is the founder of information theory. He published a paper, and oh goodness, the date escapes me.
1948 at Bell Labs.
Oh, very good. 48, yes, and he was actually trying to solve a specific problem. How much information can you transmit across a wire?
Yes, and because there's an application in telephony where you try to multiplex, that's to say, transmit more than one voice at a time on one wire, and he was trying to see how many you could.
Yes. So obviously, now this is interesting. One common theme in our Breaking Math podcast when we're talking about ideas is what led to the ideas, And in this case, of course, it was a specific engineering problem that then led to the concepts in information theory. But then from that, a new way of looking at the universe. And that is, as we will discuss in this episode, looking at the universe in terms of information.
Yes. Now, Hannah, what is your experience with information theory?
I don't really have any.
So it's not. So it's fair to say it's not part of the main math curriculum, then.
No, not at all. No.
And given what we said about how useful it can be, why do you think that might be?
I'm not really sure.
Because I have noticed that engineers and mathematicians have a lot of times very different things that they study. Information theory, however, has a very useful theoretical as well as practical aspect.
I'm wondering if it's kind of more a matter of tradition. It is a relatively new field. It's not even 100 years old at this point. So it could be that it's just a matter of tradition. Of course, it's a very, very relevant topic, and it's a very hot topic, both in physics and engineering. So perhaps that's why some folks haven't heard about it.
Now, Gideon, do you have any experience with information theory or information?
Just a very basic awareness of it. And
what is this basic awareness, sort of?
Just an awareness that information can be broken down into the smallest units, and that's about it, really.
And let's see what that is. This next section will provide an example that will illustrate for the audience exactly what information theory is. Flip a fair coin and see what it lands on. You now have one bit of information, heads or tails. Flip it again. Every 50-50 outcome gives you another bit of information. This is the true definition of a bit. Now, what happens when you have more than two possible outcomes? Say, what happens if you have a fair die? In the case of the fair die, you have about 2.7 bits of information per throw. This disparages a common misnotion about the bit, that the bit is indivisible. The reason why is this. If I told you I rolled a die, it would take you between 2 and 3 yes or no guesses. On average, 2.7 to be precise, to guess what I rolled.
Wow, that's actually a very interesting concept. So obviously I'm an electrical engineer, and information theory is very much in my future this semester, in fact. But I honestly haven't done a whole lot. I never knew that you could have a fraction of a single bit of information. So that's actually but it makes sense the way you explained it with the dice.
Yes, and of course, when you're storing information, more or less you have to have bits indivisible. When you have digital storage, you can't store half a bit on a computer.
That makes my familiarity with information storage so far was based on that, and I get it. You can't have half a bit on a computer, but you can, in theory, have a fraction of a bit of information.
Precisely. Now let's look at another scenario. What happens when the coin is unfair? Like what happens if there's 2/3 of a chance of a coin flip landing heads? In this case, there's only 0.92 bits communicated per flip. If perhaps that seems a little hard to grasp, then consider another example. Suppose a coin only lands heads up. Each flip, in that case, would give you 0 bits of information. The reason why it give you no information is because whether it lands heads up or heads down does not give you any new information about the coin flip. You already knew, before it was flipped, whether or not it land heads up. Here's something else to consider. What if you did not know that the coin was unfair? You might guess that it gives you 1 bit of information per flip anyway. This shows that estimates of information can give you a bound on the amount of information, but not necessarily tell you how much information you have. In fact, this will almost always be an upper bound, because the more you know about any system, the more you'll know about the probabilities involved. To put it another way, the more you know about something, the less random it seems, and true randomness has the highest possible information content.
Okay, so just to review those concepts, 1 bit of information as we were defined in information theory is the knowledge that you get from a 50-50 choice.
Yes. There are other units. There's the NAT, where instead of taking the base 2 logarithm, you take the base E logarithm, the natural logarithm. That's just for a more technical audience.
Yeah. Okay, I understand. Interesting. Okay.
And then there's the Hartley, where you take base 10.
Okay.
And a bit is also known as a Shannon. Hannah or Gideon, have either of you ever compressed a file?
Yeah, definitely.
Yes.
Now, as far as information theory goes, could you guess what that does?
From what you're saying, I'm taking away that the more certain and the less chaotic a piece of information is, then the less information it carries, basically.
What compression does, in the ideal case, which is impossible, is have the original information represented, the original information content. So even though there might be a million flips, you can compress that down if each flip is not a fair flip. Now, we ran a few experiments just to show you what this means in practice. And what we did was we wrote a program that flipped a coin virtually 1 million times. And the first time it was fair. We had a 1 megabyte file, and when we compressed it, it compressed to 1 megabyte as you would expect. When the probability that it would land on heads was 2/3, it compressed to 931 kilobytes. 918 kilobytes would be the perfect average. When the chance was 9/10 that it would land on heads, it compressed all the way down to 562 kilobytes from 1 megabyte, where 469 kilobytes would be the average. And when we just did 1 bit, it was less than 1 kilobyte of data that ended up on the hard drive, where 0 would be what we would expect from the formula.
All right. So in this next segment, in order to really illustrate a practical application of information theory, we're going to talk about something that I just learned about recently, and that is data compression.
And specifically, LZW compression.
Yeah, and LZW is named after 3 engineers.
Ligg, Zempel, and Welch.
Okay, very good. Yeah. And they specifically use that, their data compression algorithm is used specifically, I believe, in images currently. Is that right?
Yeah, I think JPEGs.
Okay. So those of you who use Facebook or who use many applications online, you interact with JPEGs, also other forms of images, TIFF images, GIF images, things like that. In a very general sense, when we talk about compression, essentially what this will do is an image on a computer can be broken down into single pixels.
Yes, and to explain how LZW compression works,
sure.
Let's take ABAB, that thing I said at the beginning 8 times.
That's a great example. Okay.
The first symbol will be represented as A.
Mm-hmm.
The second symbol will be represented as B.
Yes. Now, if you've got a whole sequence of them, you can, of course, as you said in that opening segment, you can say the entire sequence, which takes a lot of breath, or you can just say AB 16 times. And I don't remember what the...
And I'm pretty sure what LZW would do is say AB, then have a symbol that means AB once,
mm-hmm.
and then have another symbol that means ABA, and then BABA.
Okay. Now, real quick, so let's say that you've got a picture. Let's say that you've got a TIFF image or a JPEG image. You know, you've got a beautiful picture. If you zoom in, it's just broken down into individual pixels that are, red pixels or green pixels, your primary colors. What you can do is you can go through the entire thing, and if you have 6 green squares in a row, instead of storing all 6 green squares, as Jonathan said, all you do is you just have an algorithm that says green square times 6.
And if you think about a typical image of, say, somebody at the beach, the sky is going to be a lot of repeated things. There's going to be a lot of stuff that you could get rid of in the sand because sand looks like noise to the human eye.
Mm-hmm.
And yeah, that's another point that we could bring up is the difference between lossy compression and lossless compression. Just really quick for the more technical listeners out there. Lossy compression, you lose some of the original information, mm-hmm. but enough for a human to appreciate it. In lossless compression, which you need for something like a book, where you can't have a bunch of gibberish in the middle of it, it represents all of the original information.
Wow. And of course, the other really cool thing is, as I was thinking about this, again, my mind was blown. I just, simply put, I didn't know this. And I'm learning more and more as I delve into these mathematical topics. We do that all the time. Writing is a form of compression.
And in fact, one form that everybody in this room probably uses daily is predictive text. If you type in TEX on a keyboard, the next letter is probably going to be what, everybody? T. And if you say AAGA, it's more likely that you meant saga. Now, on our next segment, we're going to play 20 questions. The reason why is going to become apparent as we play. Now, Leela, would you kindly go to 20q.com?
Yes, of course.
Leela is going to read the suggestion. She's going to basically play the game as we say yes or no to the questions.
Okay, so I'm going to pick one of the suggestions.
But not tell us.
And not tell you. I have chosen.
All right. So what should our first question be, everybody?
Oh, gosh, this is worth discussing. Okay. So who here is good at 20 questions? I have 16 nieces and nephews. That's right. I have a huge family. I have 16 nieces and nephews. So 20 questions is something that comes up a lot on car rides. So obviously the broadest questions possible.
Now, I don't have much experience with bread boxes outside of 20 questions, but that's a traditional first question. Is it bigger than a bread box?
Oh, okay. Actually, you know what? I think that would be fine. So let's say we do a little vote here. Should we just go ahead and say, is it bigger than a bread box? I'm game. Okay, let's do it.
Is it bigger than a bread box?
Yes.
All right.
Okay.
Let's see.
Should we find the upper bound of it then? And again, I guarantee there's an algorithmic way to do this. I guess.
Well, the fastest way to do it algorithmically would be to double the thing every time. But because we're talking about colloquial knowledge, the algorithm is going to be a lot more nuanced. That's not so related to information theory as it is to computing.
You all caught that, right? Just kidding.
Well, the website recommends question 1 as, is it classified as animal, vegetable, or mineral?
Oh, okay. Well, we did the bread box one.
Should we do that? Should we go ahead and go with the suggestion?
Yeah.
Okay. So,
we're not going to take any more suggestions from the website.
Okay.
That's a one-off.
Is everybody cool with that?
I'm cool.
Yeah.
I'm cool.
All right. Is it animal, vegetable, or... Oh, wait, we can't ask it has to be a yes or no question.
I feel like animal would be the most likely most of the time.
So should we say, is it living or dead?
Yes.
Is it living or dead? Wait, is it a living?
It is living.
Yes. All right.
Okay.
So it's living and it's bigger than a bread box. So
that's a lot of options.
I know. Wait. Let's catch up. So we're at 2 questions or are we at 3?
2 questions.
Okay, we are at 2 questions right now. Narrowing it down. I'm glad I got timed here.
So it's alive. Any suggestions for the next question?
Okay, we know it's alive. What will narrow it down? We could ask how many legs it has.
Most animals have 4 legs, though.
We don't know that it's an animal, though.
Yeah, we could be a plant or it could be an insect. That's all we know. So obviously the 4 legs, I think that would rule out most insects. That would rule out, I think, let's be specific here. It would also rule out fins.
But most insects are smaller than a bread box.
Oh, good call.
And
We've
this
already...
is bigger than a bread box.
Okay. Woo, guys, this is hard. Okay, I wish we could have listeners call in. Unfortunately, we're not live here.
I vote for, is it a plant?
Okay. I don't have a competing alternative.
Is it a plant?
No.
All right, so it's an animal.
Okay. So, yeah, now an animal. Are we ruling out insects yet?
Insects are animals.
Okay. Sorry, it's been a while. I have an embarrassingly low recall of my biology. My sophomore year at high school was the last time I took biology.
Oh.
I don't know. Shame on me. I got way into physics and math, and I left my biology behind.
All right, so maybe we should ask if it's domesticated or wild.
Well, again, I think the strategy here is the broadest questions where we can rule out the most information.
Like something like, is it a mammal?
Yeah.
And you think that I like that one, and it would rule out about half of the things.
Okay.
All right, is it a mammal?
I don't know.
Oh
no.
Good one.
Oh
okay.
no.
So I guess Google to the rescue. Let's check if it's a mammal.
It's not that easy.
Okay.
So this is something that I don't know if it even falls into those categories.
Dun, dun, dun.
In that case, I feel like, is it a water animal or is it a land animal? Might be a reasonable question.
For our listeners, we just got a little bit more information than yes or no. But that's important. That's important to note. Just because now we can't say that we got 3 bits of information. We could say maybe we got 4.5. Who knows?
This is fascinating. This whole information theory. It's like solving a mystery.
It is.
It seems like not knowing whether it's a mammal or not should narrow it down kind of a lot, though.
Yeah, because it can't be an elephant. Can't be.
Yeah.
Ooh, should we ask if it has eyes?
Again,
I'm just so lost here.
I am as lost as you are. So we're all lost. If this was a high pressure situation, like
I think I would ask if it had eyes.
Gun to our head.
Because we got it pretty narrowed down already. We have like another 7 questions.
That's a good one.
Does it have eyes?
Yes.
Oh, it has eyes.
All right,
okay.
so
it has eyes, and we don't know. What was the one that we don't know? I forgot.
We don't know if it's a mammal.
Oh, okay.
Maybe we ask if it lives on land.
Okay, and that would be in question 6, right?
Yes.
We need like some scary. Can we have some like intense music during this part of the pod? You know what I mean? Like,
oh yeah, cue the intense music.
High stakes here. High stakes. I think we've got some virtual high fives here at stake.
Maybe I chose like the first one.
I want some virtual high fives.
All right, so it has eyes, so it has to be kind of a normal animal.
Unless it's not.
Oh, could it be mythical?
That's kind of a one-off. Does that rule out a lot of options?
It rules out dragons and phoenixes.
You know, you've been really leading the charge here.
All right, you lead the charge.
Oh no, I was going to say, I think I'm okay with that. With that question, I can't rule it out. You know, since it's our survival that's at stake. I'm just kidding. Since it's our pride that's at stake. Are we okay with saying, is it mythical?
I think that's a great idea.
You realize the stakes here. Okay. Okay.
We literally have dozens of seconds of shame at stake.
I know.
Now, Leela, is it mythical?
Some people think it's mythical. I think that it's real.
All right, so yes.
Okay, now, how much do we know about Leela? Because that also contributes to our information about this answer, too.
Yes, and of course, right now, we just got a little bit more than one bit of information.
Yeah, and of course, we could have been more specific about how many people know that it's mythical, you know. You know, like...
Well, I know. Okay. Let's
call it mythical.
All right, now, let's see. What mythical creatures do we know? Griffin, Bigfoot.
Yeah, definitely something that can fall in between mammal and non-mammal.
Fairies, for sure.
Fairies.
Unicorns.
Unicorn.
See. What else is maybe a mammal?
Hey, how about that Mexican one? What do you call it?
Chupacabra.
A chupathingy. That's from a very funny show online.
So should we ask if it has hair or fur?
I think so.
Should we go for fur? Well, okay, dragons don't have fur. We're saying fairies have hair and skin, not fur.
Is it mostly covered in fur?
That's the question. Okay, are you taking exact... Yeah.
What do you think about this question?
Yeah.
Yeah, no, is it mostly covered in fur? Yeah.
Okay.
Is it mostly covered in fur or hair?
No.
Okay.
Oh, wow. Okay. So now, I hope I wasn't premature in saying it's definitely mythical. Our answer was some people say so. You know, so maybe that broke...
But if there's any doubt about it being mythical or not...
Okay.
Lots of mythical animals fly.
Okay, so let's see this.
Should we
here.
say, wait, does maybe prehistoric counts as maybe mythical? But that doesn't sound correct to me.
Okay, good question. Goodness. So, can we name some things?
Let's see.
Oh, fairies, obviously.
For sure.
Okay.
Fairies, dragons.
Good. Yeah. Dragons, fairies. It's bigger than a bread box, though.
Some fairies are 4 feet tall according to mythology.
Oh, okay. But always, it was a definite answer. It wasn't an always answer or, sometimes answer. It was that was a definitive one.
But if it's a prototypical example of a fairy in her mind that happens to be more than 4 feet tall, then it would be a definite yes.
Okay. You know what? I'm feeling dragons, unless trolls or what are some Harry Potter things like
a phoenix,
an orc, a phoenix,
hippogriff,
hippogriff.
Let's see. Do a lot of these have feathers? Only one has feathers.
It's like a basilisk.
Pegasus.
Basilisk. I like that. Yep. I like it. What else?
Pegasus. Should we say, does it have 2 or more legs?
You know what? Okay, so here's the thing. Yeah. We're looking at trolls. Now
I kind of like the does it fly question.
I agree.
Let's do that one.
Okay, we're gonna do it.
Does it fly?
No, not on its own.
Okay, so I'm gonna say no to dragons.
Yeah.
Let me. Okay, possibly trolls, possibly orc. No to phoenix. Oh no, I liked phoenix.
However, we got an additional little bit of information.
Okay.
Not literal bit, but a little piece of information.
We did.
It doesn't fly on its own.
Okay.
Maybe it takes American Airlines.
Yeah.
Yes. Snakes on a plane.
In that case.
Okay, hippogriff. So we're gonna say no to that. So it could be the basilisk. Now, is basilisk only Harry Potter lore, or is that
that's a thing?
Oh yeah, that's a thing.
Okay, Pegasus. Now, Pegasus, they fly?
They're covered in fur, though.
They totally fly.
Okay, man, and fairies fly. That would be sad if you had a fairy that didn't fly, wouldn't it?
Called a sprite.
How about a gremlin? Gremlins sneak onto planes and mess
Oh
everything
my
up.
But are they bigger than bread boxes?
I think so. How
I've
big
never
is a
seen
bread box?
I don't know. I've never seen a bread box.
Okay.
I
Okay.
assume that it is.
So if this were, oh gosh, how many questions have we asked?
We have asked 6.
I think more than 6.
No, we've asked 6.
We'll go with 6.
Yeah, we'll go with 6. I should keep track of this.
6. Alrighty. This is interesting. Okay, so it's mythical again. It doesn't fly, and it's not covered in fur. What else? Okay, I honestly think that we should have a quick huddle. I'm glad we're not timed. What are some other mythical creatures? Help us out here.
I'm telling you, gremlin maybe.
A big gremlin. Okay.
A big
Elf.
gremlin. Elf. Let's see what else flies.
Maybe, a lot of these are humanoid.
I know, right? Hobbit.
Don't forget, I said, or I don't know if I should give away too much.
No, don't.
Okay, I'll just be quiet.
Don't. Okay. Okay.
Because
Yeah.
we need 20
Yeah.
bits of information, or you can have a little bit more than that.
Okay.
Okay. What else? Okay, I'm trying to help us out. Hobbit. Is that only Lord of the Rings, or is that a common thing?
I think that's Lord of the Rings. I think they're called halflings when they're not part of Lord of the Rings.
Okay. Then who runs the banks in Harry Potter? What are those things called?
Goblins?
Goblins. Okay. Those are they're small-ish.
No, do
dwarves?
goblins sometimes fly?
Not on their own.
That was very cryptic. Bleh.
Okay.
All right.
What about dwarves? Like Santa's dwarves, or Snow White and the Seven Dwarfs, or the dwarves from Lord of the Rings? Okay. Should we ask if
Oh, yeah,
these
brownies
things-
too.
I don't know what brownie?
Brownies.
What-
I don't think they're bigger than bread boxes.
They're
so.
not
that's
bigger than
true.
bread boxes.
Okay. Should we ask if it's humanoid?
I think so.
Is that a good one? Yeah. Okay. Is it humanoid?
Yes.
Sweet.
Okay. Beautiful. Okay. So now interesting questions.
Is
I
it
think-
taller than human, shorter than human? That'd be kind of a good.
I
one.
think that would be a phenomenal question.
What do y'all think?
I think you should go, is it shorter than a human? It could be giant. That'll tell us real quick. Yeah.
Is it shorter than a human?
It can be.
Oh dear.
I don't want to give out too much information.
Okay.
Do not.
Okay.
So let's.
But if I say something like it can be, that is just, I'm just curious. Is that one bit of information?
That's
It's
a little bit
than
more because a bit of information would be yes or no.
yes or no. And so
Full stop.
I want to try and answer these questions with yes or no, but some of the questions that you're asking, I can't. So I'll just say,
Which is important.
doesn't apply.
It was just important to note for natural language that a lot of times there's fractional bits. In fact, in Shannon's 1951 paper on the entropy of printed English, there is an estimate of about, I think it's around 2 bits per letter, which is less than you would expect. There's 26 letters, and log base 2 of 26, which tells you how many bits that would be on average, would be 4.7. So it shows that English letters are like an unfair coin flip, basically.
Oh wow, interesting. That's just crazy. That's just
And
crazy.
the way that he did it was this:
Mhm.
he had text, and he had people guess the letter.
Wow.
And if they could guess it correct, then they counted it, and he applied his formulas to that. But let's get back to the game.
Okay, that was a fun tangent, though. I really enjoyed it. Okay, so back to the game. We know it's humanoid, and we know it's mythical, and we know that it can be shorter. So let me go ahead and do my list one more time, and here's our current list.
Wait, so it's shorter than a human?
It can be. That's all we have.
I think an elf.
Okay. Well, what are the elves that are shorter than humans?
A lot of elves, the elves from Dungeons and Dragons.
Okay. Because in Lord of the Rings, they are like angelic humans. Okay. That would be the evolution of mythology. So it could be elves. You're right. It very well could be. What else?
I'd like to add aliens to the list if you guys agree with that.
That's a really good one because it can be mythical.
You're right. Aliens.
Although true aliens, aliens must exist based on probability, but we're not talking about probability.
I'm feeling like we take some stabs here at some of these questions. Should we go for is it an elf or is it an alien?
That will give us less than 1 bit of information.
Oh dear.
The reason why is because let's say there's 10 things.
Yeah.
If we have a 9 out of 10 possibility of getting it right or wrong, then we get 0.4 bits of information.
Oh,
So
okay.
maybe if we can split this list up into 2 categories and then ask
Binary search is the fastest way of searching with bits.
Sure, absolutely. Okay, so let me just do these are all the things. So I've got elf, I've got aliens, I have the ones in italics that I italicized. We've already ruled out. It's not dragons. Trolls are humanoid, right?
But they're bigger than humans.
Okay, so we're ruling out trolls. Orc?
They're bigger than humans.
Are they?
Yeah, they're in D&D. They're like 7 feet tall.
Oh, I didn't know that. Okay, so not orc. Okay, very good. And then after orc, we have gremlin. I think we still have. I doubt it. I don't think it's gremlin.
How about do they live on an Earth like? Actually, that only rule out aliens.
Okay, that's a good question. Okay, so here, real quick, gremlin, hobbit. Do we want to include hobbit in this?
Hobbits are always shorter.
Oh, okay. So, but they can be shorter. So I'm gonna include hobbits.
But they can be, not they are.
Oh, thank you. Good call. Not hobbits. Okay. Goblins, shorter always, right?
I don't know. I don't know what goblins are.
Dwarves.
I think sometimes they are.
Dwarves are always shorter. Cool. So aliens. So we've got three things: elves, aliens, and gremlins. We could ask a simple yes or no.
Wait, gremlins are tiny, right? They're smaller than humans.
You're right. How'd that wind up there? We've got elves and aliens. That's only two things right now.
Well, let's see. We'll split up the list. Does it live in an Earth-like realm?
Because if it's Earth-like, it could be an alien from an Earth-like realm.
Yeah. Okay. Does it necessarily live on an Earth-like realm?
May I ask? Could we just say, is it alien?
Is it alien?
Yeah.
But then an elf might be alien.
Middle Earth elves. Oh my gosh. Oh my god. Well, okay. There's no way to splice this. This is an ambiguous, murky area because the realm of fiction is so encompassing that I don't think there's a good way to differentiate.
All right. Let's just say, does it live on Earth or on a place based on Earth?
Okay.
Because if it's based on Earth, it can't be an alien.
Okay. With that understanding, if it's Earth based, like Middle Earth. Right?
Yeah, Middle Earth counts as Earth.
Okay. I get where we're going. What do you guys think? Any objections?
That sounds good to me. I can't think of myself.
Yeah, I can't think of anything.
Am I sensing some eye rolling going on? I'm just kidding. Okay, all right.
Does it live on an Earth-like realm or a realm based on Earth where Middle Earth from Lord of the Rings would be considered Earth-like in this context?
No.
Oh, so I'm thinking aliens.
Should we shoot
Definitely
for
with
it?
the shot.
Let's do it. Is it an okay? I'm gonna ask. I'm gonna hit the red button here. Is it an alien?
Yes.
Oh, yeah! Ding, ding, ding. Awesome. Okay,
Good job, guys. I chose E.T.
Awesome.
That was my
high fives all
what
around.
A cool thing. Okay, so we were gonna have to go back and honestly count how many that was. Was that even 20?
That was 8. Yes. Oh, okay. And I want to point something out for our listeners as far as information theory goes.
Yeah.
With the kind of answers that Lilo was giving us, we had a little bit more than 8 bits of information to work with. I'm guessing it was probably around 15. Because if you look at the sliding scale, that's just my intuition. I don't have any formal math to back that up. However, if we did 20 questions, because we have more than 1 bit of information per question, we can do more than 2 to, let's say we had 30 bits total. That could be up to 1 billion different things.
Wow, that's a lot.
Yeah.
And 20 questions.
Okay, yes. And
yeah.
Okay.
And 20 questions where each question isn't a strict yes or no.
Wow.
In our daily lives, we're most used to data being stored in magnetic disks or in flip-flops to be used by digital machines. Another, perhaps more covert place where information is kept is in the form of DNA. In DNA, you have 4 possible letters, A, C, G, and T, and so you have around 2 bits of information per letter. The evolution of various species and the phenomena inherent in evolution, including sexual selection, convergent and divergent evolution, and other phenomena, are intrinsic to information theory. The information contained in DNA is a simple message. It describes how to survive in the environment the species is given. So, one example of how information theory relates to DNA is in the creation of new information. And I think we should go through the process of how that directly happens.
Oh, absolutely. This is actually extremely fascinating. Okay, so just to recap, again, I am not a biologist myself. So, again, I know what you just said, that essentially DNA is 4 different starting, I guess we'll call it symbols.
Yeah, it's the chemical on the DNA. Adenine, I think, cytosine, guanine, and thymine.
Okay.
I might be wrong.
And then, of course, we just call those A, C, G, and T. And then you said earlier, you said that essentially that each letter is, as we said, 2 bits of information. Can we elaborate why each of those are 2 bits?
Yes, maximum 2 bits. And the reason why it's maximum 2 bits is because if I think A, C, G, or T, you can ask me, is it A, C, or is it G or T? And I say it's A or C. And then you say, is it A or C? and I tell you A. So it takes 2 yes or no questions to determine each letter on the DNA.
Oh, that's right.
Because
Okay.
A pairs with C.
Okay.
And G pairs with T.
Well, that's even if it didn't pair, the fact that there are 4 of them means that it's 2 bits.
You know what? I think from a previous conversation, this is going to help explain it very well. Okay, so you said that there's 4 letters. If we only had binary digits, ones and zeros, we could do a maximum of 4. We have, with a 1 and a 0, you could do 0, 0. You could do 0, 1. You could do 1, 0, and you can do 1, 1, and that's it. So because of that, that's a maximum of 2 bits per letter.
And in the scheme, you could assign A to 0, 0, C to 0, 1, G to 1, 0, and T to 1, 1 if you were so inclined.
Cool. Okay, this is great. This makes sense. I think I understand it quite well now. All right. So then, as you said earlier, DNA and biology, that's the language for life. That's everything we see, all of our traits, and it's quite mind-blowing. Everything from the color of our eyes to traits that we have, the kind of body type we have.
Yes, and what we don't need to use anymore. For example, whales don't need their hip bones for the same things that they used to use it for, so there's information arguably lost there.
Wow. Okay. I'm still wrapping my mind around this whole fact that those 4 letters, those combine into the traits that we see now. Oh, it's just mind-blowing.
Now, one interesting thing is that amino acids are represented by one of 25 characters, typically. A, C, D, E, F, G, H, I, K, L, M, N, P, Q, R, S, T, V, W, Y, and $sign.
Ooh, that's a mouthful.
And what's interesting about this is that the amount of pairs in a DNA sequence is not necessarily the amount of information in DNA. In fact, it's almost always going to be a little bit less than that, because you have things like what used to be called junk DNA. And like virus markings in DNA.
Okay, now correct me if I'm wrong. Again, I'm not up to date here. So is what was once called junk DNA? Is it still junk DNA, or is there?
There are certain purposes for that. I can't recall what they are.
Okay, very good.
So when we talk about, for example, in the Buchnera chromosome, there are approximately 760 million base pairs, which translates to 3.53 billion bits of representation, roughly. But the amount of information contained is no more than 3.11 billion bits. That's a discrepancy of about 0.42 billion bits.
Oh, wow. That's a mouthful. So how do we break that down for our listeners?
Well, it's just an example of how there's less information contained than in the representation, which is always the case, basically.
Okay. Just to clarify as well, again, we already established for those who are less knowledgeable about biology, such as myself, we already established the 4 letters in DNA. You also said base pair. Can you clarify what a base pair is?
Yes, A, C, G, or T.
Just a single one of them.
Yes.
Oh, okay.
It's called a pair because the letters pair with each other.
Cool. Very good.
Now, one way that humans create information when they breed animals is by deliberately using inbreeding. And the reason why this works is because when you have 2 sets of DNA that are very similar, anything created is going to be a mutation. That's why it works. So you take these horribly inbreeded horses and you breed them with healthier horses to get the traits that you want. It's
my gosh, I had no idea. Wow. So okay. So then, just to clarify, all I know is that of course, inbreeding is very much discouraged, and I've heard in a very general term why that is. So let's just say, for example, if you have 2 first-generation inbred horses, I wonder what kind of possible mutations you can expect, or even a second-generation inbred horse.
Well, I don't know too much about horses, but in humans, one generation of inbreeding is likely to produce heterochromia, which is eyes of 2 different colors.
Oh my gosh. Oh, wow. Okay. And when we say one generation of inbreeding, that is specifically a brother and a sister who would then reproduce and have a child.
Brother and sister are multiple first cousin marriages.
Okay. I wasn't sure. Now, real quick, sorry. Are multiple first cousins less dangerous than brother and sister? Because you seem
Yes, they're brother and sister. The inbreeding coefficient is 0.5.
Oh gosh. Okay.
With first cousins, it's something like an 1/8.
Okay. All right. So then this inbreeding is a very intentional thing with respect to horses.
Yes, it's designed to create new information, new traits that weren't there before.
Okay. So we create new information with DNA through mutations. Okay.
Yes, and this increases the chance of a mutation happening, especially because all changes are more likely to be mutations than not after a certain amount of generations of inbreeding.
Wow. Okay. Wow. Interesting. This is all fascinating about the creation of information through breeding. Okay. And then obviously this is done for a purpose. So the hope is that we understand scientifically that you're going to have a lot of mutations that are not beneficial, but you will have mutations that are beneficial.
Yes. An example of a non-beneficial mutation in most species is albinism. If a creature is albino, then it's more likely to be seen in its environment and it's more likely to be eaten. Mm-hmm. An example of a beneficial mutation would be, for example, when the mole lost its eyes, you have less chance of infection.
Okay. Oh, okay. Interesting. Do we know, with respects to horse inbreeding, may I ask what's an example of a beneficial mutation?
Oh, it could be anything from coat to trainability to any number of traits that horses are bred for.
Okay, wow, this is just fascinating. I know that with respects to dogs, historically, I believe that Shar-Peis were specifically bred so that when they're bitten, it didn't slow them down or inhibit them, because basically they've got rolls and rolls and rolls of skin. So even though they are absolutely cute, the intention behind that was...
And dogs are a specific example of how DNA is very programmable, actually. Dogs and fruit flies and a couple of other animals, just a handful of animals, fall into a category of animals with slippery genomes.
Okay. What do you mean by slippery genomes?
For example, there's this one set of base pairs in a dog's DNA that if it's only repeated a few times, the dog has a upturned snout. If it's repeated more times, it has a downturned snout.
Oh, wow.
So it's very programmable. Dogs are extremely programmable.
Wow. Man, is in this information age, what we find out about DNA and exactly what bit is responsible for what traits is just fascinating.
Especially when we unlearn it all the time, when we realize that one gene is really not responsible for all incidents. It's a feedback system and it's highly nonlinear, but that's outside the scope of information.
That's a fascinating thing, though, for correctness. We think we know one thing, and then, we find out that the system is more complex than we originally thought.
Oh, yeah, and DNA is orders of magnitude more complicated than even general relativity.
Goodness. Yeah. Wow.
Information normally comes from the sun when you're talking about DNA, or the creation of information requires energy. And for example, when you had the Cambrian explosion, which was when a few creatures turned into a lot of different types of creatures by mutating all over the place, you had the creation of a huge amount of new information.
Wow. Okay. Now, this is something that's quite interesting. So if I'm not mistaken, when we're talking about information as we are, we can say it is interchangeable with energy. Is that correct?
In a certain sense.
Okay. All right. Yeah. This is just new in talking about, information available or the creation of information. You said earlier that, so energy obviously comes from the sun. And you also said that that's responsible for the Cambrian explosion.
Along with just the natural process of evolution, yes.
Okay. And then, of course, the increase in information we are attributing to mutations, and then we get our present biodiversity.
Exactly.
Wow.
In 1941, Jorge Luis Borges imagined, in La Biblioteca de Babel, or the Library of Babel, a library with all possible books. This story has direct relevance to information theory. Let's see if you could catch it. A short excerpt will be read in the original Spanish and in English. A cada uno de los muros de cada hexágono corresponden 5 anaqueles. Cada anaquel encierra 32 libros de formato uniforme. Cada libro es de 410 páginas. Cada página de 40 renglones. Cada renglón de unas 80 letras de color negro. También hay letras en el dorso de cada libro. Esas letras no indican o prefiguran lo que dirán las páginas.
Now, in English, Each wall of each hexagon is furnished with 5 bookshelves. Each bookshelf holds 32 books, identical in format. Each book contains 410 pages. Each page, 40 lines. Each line, approximately 80 black letters. There are also letters on the front cover of each book. Those letters neither indicate nor prefigure what the pages inside will say.
Now, if you didn't catch it, the significance of that was that there are all these possible books. And the number of possible books, the number of books in this library, relates directly to the amount of information contained in each book.
This is an absolutely fascinating read. I've seen this short story brought up in philosophical circles and in English classes. I think everyone, if they have a chance to, should read it. That and everything else, right? I just love it. The whole idea of an entire universe with books about everything. And as far as they know, it's an infinite universe. Is that right?
Well, as far as they know, they think it might be infinite. If they were infinite, then they would have duplicates of the books because there's a finite amount of possible books.
That's right. That's right. All the citizens of this world that is a library, they all live in these little hexagons. They're allowed to move around and they discover new information. And it's interesting because they talk about one of the great discoveries is that they have, 25 letters?
Yes. If you do the math, that's about 10 to the 1.83 million different books possible.
Wow. Okay. Throughout this short story, we're introduced to a few ideas. Like, apparently a lot of the books in this library seem to be quite randomly put together without meaning or purpose. And we can see the immediate philosophical discussions for our world.
And also, there's going to be a book where it's absolutely perfect, everything that's in Hamlet, except at the very end, there's just a random Q.
Oh, wow. Wow, this is interesting. That reminds me of that old analogy about if you have a room full of monkeys, eventually they'll write the completed works of Shakespeare. So this is a great discussion on randomness in mathematics.
And of course, if you wanted to find a book in this library, you'd already have to know what's in the book. Because the thing is, there's no information about anything in the books because it's all possible books. There's no constraint of language. There's no constraint of content. That's why this library is almost useless.
Wow. Not to get cynical about it.
Oh, no.
Yeah. But wow, that's just fascinating. And I think it's fascinating that we bring up this short story in our podcast because, of course, this entire story is based on information and our episode is based on information and the attempts at describing our universe in terms of information. So,
yes. And what's interesting is that somebody might ask, well, can't you compress the books anyway? And it's like, yes, you can. However, the average size of the books will be the total amount of information in each book, which is, for those interested, around 6 million bits.
Wow. Now, this book itself, it has quite a few themes. It talks about, of course, information meaning. It talks about randomness. It talks about mathematical concepts and infinity, I believe. And I don't want to spoil the ending of that short story. Our listeners may want to read it, but he has a very interesting idea about infinity and set theory, and that he talks about in the very, very last paragraph.
And for those who are interested, it's written by Jorge Luis Borges. That's Jorge Borges, and it's called La Biblioteca de Babel, or the Library of Babel. Information not only rules our lives, but as we've seen, rules life itself. And as we learn more about this nascent science, we will learn more about ourselves. We've explored the realms of fiction, of life science, of computers, and of the spoken word. We hope that the pervasiveness of the science is self-evident. I'm Jonathan.
And I'm Gabriel. And unfortunately, Gideon and Hannah had to leave, but we thank them for their contributions.
And this has been Breaking Math.